Consider a mass spring system. M equal to 2, so mass equal to K equal to 32. So the spring constant is 32. Determine if pure resonance occurs when the system is driven by the following periodic forces. T equal to 2 pi. So for the first information here, we have mass equal to spring constant K equal to 32, mass and spring. You can find out the natural frequencies of the system, of the mass spring system of the system is omega naught equal to square root of K divided by M. So square root of 32 divided by 2, square root of 16, which is 4. So from that data, we know the natural frequency is equal to 4. Determine if the pure resonance occurs or not. First case, square wave. So note that pure resonance occurs when there exists a component of the force with the frequencies matches the frequencies of the system. So there exists a natural number n such that omega n equal to omega naught. So omega n is a frequency given by the force, one component of the force. And this one, omega naught, is a natural frequency. In our case, this is 4. Now let us look at the frequencies that's given by the force. In our first case, we have a square wave. So the force is given by this equation. This one, the force is given by is equal to 1 if t between 0 and pi, 0 here, pi here, equal to 1. T equal to minus pi to 0, then you have minus 1. And you extend it periodically. So you see that the force is odd. So F is odd. So this function is odd. We know that if we write down F in terms of Fourier series, we only have the side terms. Fourier series of F. The Fourier series of F contains only side terms. Ft equal to the summation n from 1 to infinity bn psi n pi t divided by L. In our case, L is half of the period. So here's a question give us t equal to 2 pi. The full period 2 pi. So L is half of the period. L equal to 2 pi. In this case, L equal to pi. These terms, n pi divided by L, is our frequency. Omega n equal to n pi divided by L. N pi divided by pi equal to n. These are frequencies given by the force, with the condition that the coefficient Bn here is up here. So for example, if Bn equal to 0, that means this frequency does not appear at all. So if Bn is non-zero, there will be a component with frequencies omega n. If Bn equal to 0, this component with these frequencies does not even appear. Now we see that the natural frequencies is given by 4. So pure resonance occurs when we have that. So we need to see that whether there exists omega n so that is equal to 4. Possibly, because omega n equal to n. Whether there exists natural number so that omega n equal to omega naught. Omega n equal to n by this one. Omega naught equal to. So there might be pure resonance. Under the condition that the coefficient corresponding to that omega n is non-zero. We need to check if Bn is non-zero. And if the answer is yes, if Bn is indeed, or before in our case, because n equal to 4 here. If before is non-zero, then pure resonance occurs. And if Bn is equal to 0, before equal to 0, no pure resonance. So you see that if it is 0, there is no such wave appears at all in the forks. So that means that we don't have this match. Now we need to compute Bn, or before in our case. Bn here is given by Fourier coefficient. Bn is 2 divided by L. General formula is 0 to L. Ft psi n pi d divided by L dt. So in our case, this is 2 divided by pi, 0 to pi, Ft equal to 1. Ft equal to 1. Side n pi d over pi dt. 2 divided by pi, 0 to pi, psi nt dt, which is 2 over pi minus cosine nt divided by n, 0 to pi, minus 2 over n pi. Inside you have cosine n pi minus cosine 0. Cosine 0 is always 1. Cosine n pi, so cosine n pi is here, equal to 1 if n is even, and cosine n pi is equal to minus 1 if n is odd. So you see that this one will be minus 2 over n pi multiplies, if n is even, this is 1 minus 1, 1 minus 1, which is 0 if n is even. And if we want to compute it for n is odd, you get some number. We don't need to compute that. We only need to care about whether before is non-zero or not. But before 4 is even, before equal to 0. Bn equal to 0 when n is even. So we know that before equal to 0. So we don't have the wave with frequencies 4. We don't have such n comes from the forks so that omega n equal to 0, because the coefficient of that wave does not appear at all in the forks. So in this case, we conclude that no pure resonance. So that is the first case for square wave. Now let's try with the second case, the Sawtooth wave. here's the second part. We still have the same natural frequency of the system equal to 4. We have this force F equal to T, for T between minus pi and pi. So Ft on that period from minus pi to pi look like that. So you can see here the function F is still odd. F is odd. And therefore the Fourier series of F contains only psi terms, Bn psi n pi t divided by L. We know that this one is also summation Bn psi L equal to pi. So n pi t divided by pi is still Bn psi nt, n from 1 to infinity. So omega n equal to n. This one equal to omega naught equal to 4 if and only if n equal to 4. We need to check if B4 is non-zero or not. If B4 equal to 0, no resonance. That is the case we've seen before, no resonance. If B4 non-zero, then pure resonance. Pure resonance occurs. So we need to check that. Let's compute the coefficient Bn for this force. Bn equal to 2 over L. General formula is 0 to L. Ft psi n pi t divided by L dt. In our case, 2 over pi, 0 pi, t times psi n pi over pi, so nt dt. You need to compute this by integration by part. So let me do it. U equal to t, dv equal to psi nt dt, du dt, v equal to minus cosine nt divided by n. With that, you get this integral. 2 over pi still there. uv, which is t cosine minus cosine nt divided by n. uv 0 to pi minus 0 to pi v du, v du dt. So this I applied integration by part. Now you compute this. 2 over pi. Inside you have 1 over n minus 1 over n still there. Minus 1 over n multiplies with pi cosine n pi minus 0. That for the first term. For the second integral, you have integral 0 pi 1 divided by n cosine nt dt. 2 over pi minus pi divided by n cosine n pi plus 1 over n sine nt divided by n 0 to pi. We have quite a lot of computation. Minus pi divided by n cosine n pi, as we talked before. It is either here or here. Cosine n pi equal to 1 if n is even. Minus 1 if n is odd. You can write down as minus 1 power n. So if n is even, this number becomes 1 power even, which is minus 1 power even, which is 1. If n is odd, this is minus 1. So you can write as minus 1 power n. Second term's 1 over n squared sine n pi minus sine 0. Now for this one, we need to look at sine n pi. Sine n pi equal to 0. This term is always 0. Sine 0, 0. So you have 2 over pi. I can pull this minus 1 into this minus 1 to the n. So you have pi times minus 1 power n plus 1 divided by n. Pi and pi cancel out. This gives us 2 over n minus 1 power n plus 1. So this is our Bn. So in our case, we need to compute B4 and check if it is 0 or not. B4, 2 over 4 minus 1 power 4 plus 1. This is non-zero. And with that, you know that omega 4 up here in the forks matches the natural frequencies of the system, and thus gives the conclusion pure resonance. Occurs. So in summary, you need to compute the natural frequencies of the system, which is easiest part. Then you write down the Fourier series of f, and you see the frequencies comes from the forks. See whether there exists a natural number so that these frequencies equal to the natural frequencies of the system or not. If there is such an n, so there might be a chance pure resonance occurs. You need to check further if the coefficient of that wave with that frequency is equal to 0 or non-zero. If the coefficient is non-zero, that means that there exists a component of the forks matches the natural frequencies of the system, and in that case you have pure resonance.